The title is A Dynamic Approach Towards NOC Performance Verification in Pre-Silicon and Overcome the Traditional Overheads. Authors are Suresh Vasu, Zafar, Qureshi, Mohammad, and Thirumala Chakravarthy from Intel. Again, as a reminder, we have allotted 20 minutes for video presentation by the authors, followed by 5 minutes of Q&A. Please use the Q&A tab on your screen to post questions as we go through the presentation, and I'll read those out for authors to answer at the end of the presentation. Also, there is a poll option with the Q&A tab. Please provide your inputs, ratings for the paper at the end of the presentation. Okay. So with that, over to the Intel team. Please go ahead.
Recording in progress.
Hi, good evening. I am Thirumala Chakravarthy. I am representing Intel Technologies. Today I am going to talk about a dynamic approach towards NOC performance validation in pre-silicon and how to overcome traditional overheads. My co-authors are Suresh Vasu and Mohammad Zafar Qureshi. Firstly, I would like to talk about the motivation behind exploring a new solution for NOC's performance validation. First thing being the complexity. As the complexity of SOCs are increasing, where we can see there are the number of IPs that are included in these SOCs are getting higher and higher, and the demand of each IPs having higher throughputs, higher bandwidth, and lower latencies, and the way each of these IPs are communicating with each other on the SOC are becoming complex day by day. So this means there is the NOC's complexity has been increasing, and then equally the functionality and performance validation of these NOCs. And there are diverse ways in which these NOCs are integrated. So with each of the differing ways of NOCs integration, the approach that we are taking for NOCs validation, both functionally and for performance, is going to vary. And this calls for a ready-to-use solution for performance validation. And there are manual efforts involved in traditional approaches. Say when we talk about waveform debug or waveform analysis, it involves waveform analysis at each different interfaces. And then obviously it is error prone, and we cannot consider this for a standard validation flows. Other ways to have scripts generate the necessary matrices for performance validation. Again, when we talk about scripts, there's so much of manual effort involved, and with a requirement of any new metrics for performance validation, each of these scripts should be reworked on, and the data dumped out of these scripts should also be correlated with the waveform, and then validate whether the data that we are getting from these scripts are as per what we are seeing on the waves or not. So again, both of these waves are error prone. And one more very important aspect when we talk about performance validation is reporting. As we need to share this data across the teams. There are multiple matrices involved in performance validation, and each of these matrices should be shared across the teams whenever there is an issue, or to sign off that we are meeting all the necessary bandwidth requirements. So in such requirement, the reporting needs to be very crisp, and it should also involve actionable data for each of these teams. And next comes the debug part. So whenever we come across any bandwidth drops, we need to make sure that we need to find out which of the interfaces is adding to the latency and contributing to the bandwidth drop. So a solution which would ease the debug is a welcome change for performance validation. Apart from the challenge that I spoke about, there are a few more challenges involved in performance validation. Say, there are established approaches or established solutions for different flows of validation. Say it could be functionality validation or clocking or power validation or security and safety. We have different established solutions, which is not the case with the performance validation. So, though there are a few solutions that they are still in nascent states, and still they have to become established solutions in the industry. And we know performance is a very critical aspect and a complex one to validate as well. And any late performance bugs would lead to would prove it very costly for the product, and as well as in few cases it may also lose the competitiveness of the product itself. And we need a scalable framework for performance validation for different scopes of validation, say from IP to SOC or IP to subsystem SOC. We need a scalable solution for performance validation. And any of these frameworks which could help in performance debugs would be great. And any of these traditional approaches or lack reusability aspect. So whenever we want to work on a new NOC architecture, it again calls for a from scratch build-up of a complete NOC validation, performance validation environment, which is a very time-consuming process. And any framework that could be used across the products could be great for time as well as accuracy of the validation as well. And looking at the NOC architecture itself, here I am showing a generic NOC architecture where we can see there are multiple subsystems and multiple subsystem NOCs, and these different NOCs connected to a central NOC. And we can see that there are so many ports coming into these NOCs and then going out of these NOCs. And each of these interfaces could be demanding higher bandwidth, and which means that the NOC should be capable enough of handling all this parallel data and at the bandwidths required. So, and one more thing we can see is, say if we are talking about transactions going from subsystem 2 to subsystem 4, there are 3 NOCs involved here. So, whenever if we see a bandwidth drop in this path, it would mean that we will have to go through each of these interfaces in waveforms and then figure out which of these interfaces is contributing to the bandwidth loss. So this is a very time-consuming effort, I would say, if you have to do bandwidth waveform debug of each of these interfaces. So coming to the solution that we used, this involved usage of VIP monitors across different interstate interfaces. So the data dumped out of these monitors in form of FSDPs were fed to performance analyzer, which is a solution that we use to get rid of the traditional approaches that we had for performance validation. So once we fed all the FSDPs to the performance analyzer, it would dump out very meaningful and usable data, which we can see on the right of the screen. So in this screen grab, we can see the different matrices that were dumped out of this performance analyzer. Here we can see we have average read bandwidth, average read latency, max bandwidth, min bandwidth, and then max latency and min latency numbers for the interested interface. How this solution is going to address the different challenges that we spoke about in previous slides is: one, it is a common framework that can be used across the scopes of validation. So the VAPs are going to be common across the scopes, and the usage of these VAPs are going to be same. So just enabling this framework across these different scopes of validation would give us the required performance analysis data. So as we can see here, the same framework is used for NOC IPv level validation and subsystem level validation and SOC level validation. And the data generated out of this framework is standard and then user friendly. And the report generated out of this is very crisp and then can be shared across the teams. Speaking of the results that we achieved using performance analyzer as below. So we were able to save nearly 35% of our performance validation time. And it reduced manual efforts drastically. And data analysis became very easy. And even the data that we shared across the teams became very actionable, and then we were able to take the right decisions at the right time to eradicate any misses or any late bugs in the cycle. And we were able to find critical RTL design issues, and then the NOC issues that were that became part of it as part of generation itself. In conclusion, I would like to say that performance analyzer was very easy to enable, given that in most of our validation we would be using different VIPs, and then just plugging in performance analyzer to use this use the data that is created out of these VIPs, and then have the accurate and then precise reports generated out of it. It was a very very accurate validation experience, and it reduced the performance validation complexity drastically. Because as we were moving from scope to scope, we were not actually redoing the framework build-up work again and again. We were readily using the given framework, and then we were just it was a kind of plug and play approach for performance validation. And it reduced manual efforts wherever we were doing complete waveform analysis from the start. Instead of that, what we started doing was we were relying on the reports generated of this performance analyzer, and then only when we only on need basis we were going to the particular interface and then do the waveform analysis. And one more thing is, if there is any particular interface that we are interested in, we were just plugging in the monitor there and then using that data for performance analysis. Where in the traditional approaches, even though if we had plugged in the monitor, we would be again relying on the tracker data, which is very crude, or we would be relying on the waveform. Again, it's a very time-consuming and higher prone approach. yeah, as I just mentioned, the validation became very error-free, and then the reports were very precise. And the framework was of great assistance for debug as well. It minimized our debug cycles drastically, and then we were able to save so much of our time in debug. And one more thing I would like to add is the time that usually that would go in enabling a framework in traditional approaches was used for finding more bugs early in the cycle. So saving this initial time was of great help for us to eradicate any late performance bugs. Thank you.
Great work, guys. Maybe one question from my side, just I think we still have time. So I think the idea of using VIP monitors, I think it's a great idea. You can, I think you showed it, it gives you latency bandwidth statistics at all interfaces. So it's very clear that it can immediately red flag when you see a lower performance in terms of expected lower bandwidth or higher latencies. But can you elaborate a bit that once you do find a problem with the AHP monitors, then what approach do you use to drill down to the root cause, which may be some microarchitectural issue in the interconnect or some topology problem? So if you could just say a few words on how you, having the AHP monitor, once it flags you an issue, how do you go about from that to root causing and fixing it? I think you mentioned you found RTL issues as well, right? So.
Yeah. So one thing that we did was once we found out if there is a performance shortage anywhere, the first approach was to see at the interface level itself if we can figure out what the issue is, or in case if it turns out to be somewhere deep inside the hierarchy, we were picking out a few interfaces that we suspect, like wherever the clocks are crossing or any such interfaces where bottleneck could be present. There we were having monitors to dump out the additional data. So that is one more that we were relying on. And if it were a straightforward approach, then if it were a very straightforward problem, then we were relying on waveform debug completely.
Okay, no, that's great. So, I think this is a great way to improve the turnaround time in performance verification. So, do you guys have any further recommendations, any ideas of how to make this process more scalable, more robust? Any suggestions or thoughts?
One thing that can be added here is the integration itself could become more seamless. Say from integration to usage level, if this becomes a single framework to use, this would be a great this. Yeah.
Okay, yeah, perfect. All right, again, a big thanks to all the authors here. Really good work, guys. Thanks. So with that, we've come to end of this session. Thanks for everyone for attending, and I think there's a break. At 11:30, there will be a panel discussion on verification challenges and solutions. So request everybody to join that. And again, thanks for attending, and have a great rest of the day. Thanks.